name is Jason Senga, and on behalf of TA Instruments, I'd like to welcome you. Thank you for joining us to this exciting new product and applications webinar. Today's speaker is Dr. Bharat Rajram. Dr. Rajram is a product specialist within the Rheology group at TA Instruments with responsibility for both the rotational rheometers and dynamic mechanical analyzers. Dr. Raj Irvine. Within the product management group, he combines his extensive experience in materials characterization with feedback from customers to help define and guide new product development. The title for us webinar today is Connecting Polymer Processing and Product Performance through Rheology and DMA on the new Discovery Hybrid Rheometer. During this webinar, you can submit questions, and after the talk, we'll answer as many as we can in the right-hand corner of your screen. If you click on that icon, you will find web links and PDFs of interest available to you. With that, I'm going to hand it off to Bharat. The stage is yours.
Thank you, Jason. Hello and welcome everyone to today's webinar that focuses on polymer processing and product performance and how you can quantify that through rheology and DMA measurements. Start by looking at a quick overview of what rheology is and what kind of problems it can help to solve in your lab, and then dive right into how you can characterize polymer melts through rotational rheology, specifically looking at effects of molecular weight and molecular weight distribution. After that, we'll look at extensional flows that are encountered in processing and looking at the effects of long chain branching. And finally, we'll close out by characterizing solid samples using dynamic mechanical analysis, where we'll look at polymer chemical structure and its impact on mechanical properties of solids. So what is rheology? Rheology is broadly defined as a science of flow and deformation of matter, and it has an impact in a wide number of products that we encounter on a daily basis, whether it's food products, personal care products, or solid materials. Each of these has some element of viscous and elastic behavior in them, and rheology helps us to quantify that behavior. So if you take that toothpaste example in the morning, or the inks that are shown in the picture, you need to apply a certain amount of stress to squeeze the paste out of the tube. For the toothpaste, once it comes onto the brush, it must build up its structure really quickly so that it does not sag, and rheology helps us understand that type of behavior. So if we look at the viscoelastic spectrum, materials can either be purely viscous liquids that are described by viscosity, a single number, or they could be rigid solids that are purely elastic in behavior and that are described by the Young's modulus. But in the real world, materials tend to have some combination of viscous and elastic behavior, and we tap into additional parameters to help describe this behavior. These include the storage and the loss modulus. The storage modulus describes how much energy put into a material is lost or viscous due to viscous behavior, whereas the storage modulus, G prime, talks about how much energy is stored in the material when you impart it to it. And as you march along the spectrum, moving from viscous to elastic, Materials that are primarily viscous will tend to have a loss modulus that is greater than the storage modulus. As you start to get towards the solid end of the spectrum, the storage modulus tends to be dominant. So one way to think of these parameters is the storage modulus describes how liquid-like your material is, and the storage modulus describes how solid-like your material is, and the loss modulus describes how liquid-like your material is going to be. The other parameter that we will use today in today's talk is tan delta, and that is the ratio of the loss modulus to the storage modulus. So what do we do through rheological measurements? We measure flow and deformation and measure parameters like viscosity, elasticity, viscoelasticity through the storage and loss moduli, and damping. And know that these parameters that we measure are at a fundamental level caused by things like molecular weight distribution, the molecular structure and branching, the presence of fillers or additives, and relative concentration and the level of dispersion. And by measuring these quantities and knowing that this is where those numbers are coming from, it allows us to understand and predict processing characteristics, product performance, and how that performance is going to change as a function of temperature. So what kind of problems does rheology help you solve? Rheological measurements help deliver insights into materials, whether it's from process optimization or product performance. When looking at process optimization, it helps us understand how we can make this product more efficiently, whether it's injection molding, film blowing, curing thermosets, or something like additive manufacturing. In each of these manufacturing processes, the material goes through some sort of a stage where it has to flow, and that flow behavior is captured through viscoelastic testing and rheological testing. When we look at final product performance, the functional performance, how does this product perform? Rheology helps us understand that too. For polymer materials, we are mostly looking at solid type materials and trying to understand things like how rigid is my material? Is it flexible at my operating temperature, or is it going to be very rigid? What is the level of impact resistance that it has? Is it going to hold up to repeated stress strain over multiple times? Those are the types of questions that rheology will help us answer. And more importantly, rheological measurements allow us to go beyond basic technical data sheets. So if we pick up a data sheet for a polymer melt, we can see some properties that are listed on there. Usually melt flow rate is listed along with maybe a deflection temperature under load. And these are basic data points that help to characterize incoming material, to distinguish between one supplier and the next. But it often does not give the level of detailed information that is needed to differentiate between materials, or if you end up choosing that supplier and you get problems, it's not nuanced enough to help you troubleshoot problems. And the reason for that is these are simple basic measurements. Both of these are constant stress based measurements. The melt flow index, for example, you have a weight that is applied to the melt, and then you measure the weight of the polymer that is extruded over a period of 10 minutes, and different grades will have slightly different melt flow indices. And we'll see why this is not enough to understand our materials. And why is that? It's because viscosity is not a constant value for polymer melts. Inherently, polymer melts show non-Newtonian behavior. And what that means is that viscosity changes as a function of shear rate. The plot on the left shows the viscosity as a function of shear rate for a polymer melt, a typical representation. And we start at very low shear rates. And at this point, the viscosity is in what's called a Newtonian plateau. We call it the first Newtonian plateau, where the viscosity is more or less independent of the applied shear rate. And this is the place where the viscosity measurement is most sensitive to molecular structure. As you start to increase the shear rate, you enter the region of compression molding and extrusion, and we start to see shear thinning or power law behavior, where the viscosity decreases as a function of the applied shear rate, making it easier to process the higher the shear rate that's being applied. And then all the way at the other end, we see another Newtonian plateau at very, very high shear rates, the range that is typically encountered with blow molding and injection molding. So called out on this plot are two techniques. So when measurements are made on a rotational rheometer, we tend to apply a steady shear and make the viscosity measurement. With polymer melts, there are some challenges, especially around polymer melt fracture as we get to higher shear rates. So there are two tools that are available to the rheologist that we can tap into to get a full flow curve spanning several orders of magnitude. And we look at these briefly in the following slides. The first is the application of Cox-Mertz rule to be able to get polymer melt viscosity at very high shear rates. And what this does is it's an empirical relationship that applies for many polymers, and it takes a dynamic frequency sweep. A frequency sweep is a very basic experiment on a rotational rheometer where the rheometer head is moving back and forth in a sinusoidal fashion, very small amplitude deformations that gives us a wealth of information about its structure. And from that type of experiment, we can get the complex viscosity as a function of angular frequency. The Cox-Mertz rule tells us that the complex viscosity plotted against frequency correlates directly with the viscosity as a function of shear rate, which is what we would expect to get at as the ultimate point, which is a flow curve. You need to get viscosity as a function of shear rate. And the Cox-Mertz rule tells us that you could do an oscillation experiment, collect complex viscosity, and that essentially translates to shear viscosity. And here is an example of that. So we're looking at PDMS in this case. The red curve shows viscosity data that's obtained through a traditional flow experiment. And we can see as we start to get to a shear rate of about 1 to 10 in that range, there's deviation from the expected trend, and that's because of edge fracture, and that is not desirable. So that imposes an upper limit on how high we could go in shear rate through traditional testing methods alone. By applying Cox-Mertz and converting a frequency sweep, we can see that we can access now shear rates as high as about 500, 600 inverse seconds, almost 2-3 orders of magnitude higher than what's accessible through traditional testing alone. And there is also good overlay between these two plots, which gives us confidence that the Cox-Mertz rule works for this type of materials, and it's been applied to several different types of polymer melts. The second tool that we look at is time temperature superposition. And what this does is it allows us to extrapolate properties to timescales that are outside the instrument's range. This works by taking a series of frequency sweeps at different temperatures, and we start by shifting the frequency sweeps along the frequency axis to get an overlay between one temperature and the next. This demonstration here is showing this for storage modulus, but the same principles can also be applied for complex viscosity. And what we do is to essentially create a single master curve that now spans several orders of magnitude for the parameter that we're interested in, whether it's storage modulus or complex viscosity. And then now this gives us the original data spanned 2 orders of magnitude. The master curve that we can get from it goes nearly 7 to 8 orders of magnitude, spanning very short time scales to things that are very, very long time scales that would take several years to measure if we did an actual experiment at that time point. The master curve is very important because it gives us information about the molecular weight distribution. It gives us information about the time-dependent elasticity. And then with solid materials, it's also used to predict the long-time creep response over the span of several years, which cannot be done experimentally. So with those two techniques in mind, the application of Cox-Mertz and time temperature superposition, we look at how we can start relating, understanding polymer melt rheology better. The first thing we look at is relating polymer melt rheology with the molecular weight. And for most polymers, industrial polymers of relevance, we are operating in a range where the molecular weight is high enough that it is above the entanglement molecular weight. And within this region, there is a direct dependence between the zero shear viscosity, which is the viscosity at very low shear rates, and the material's molecular weight. At a fundamental structural level, one can visualize these types of materials, polymer melts, as a bowl of spaghetti, essentially, where the polymer chains are just like the spaghetti in the bowl. The longer the molecular weight, the longer the length of the spaghetti. And this is the reason why we have a very strong dependence between molecular weight and the zero shear viscosity. A typical scaling factor that shows a power law behavior, and a typical scaling exponent for that power law behavior is on the order of 3.4, and that exponent has been observed across several different materials. So here is an example of data that demonstrates this, and we look at the same SBR example at several points during this talk, showing 4 different molecular weights, and I call your attention to that low frequency, low shear rate range for these materials. And you can see that the zero shear viscosity plateau is significantly different across all these 4 types of materials that we looked at. The inset plot shows the zero shear viscosity plotted against molecular weight, and we extract a scaling coefficient of about 3.1 for this type of material. The other thing is the high frequency behavior is more or less independent of the molecular weight. They all collapse onto essentially the same point, and that is the point at which your capillary rheometers are operating. So if you were to go purely based on capillary rheology alone, all of these materials would essentially look the same, and that would not have the level of nuance needed to tell these different materials apart. Another thing with the melt flow index is worth pointing out here. Melt flow indices are inherently constant stress-based measurements, but viscosity, as we've seen for polymer melts, is non-Newtonian. So it is probing at different shear rates, and the application extrusion processes are always rate dependent. You're moving the product through the process at a constant rate. So a melt flow index is going to probe at different points along that curve instead of giving you a point at exactly the same shear rate when you're comparing different materials. In addition to the molecular weight, the distribution of molecular weight also has an influence on the viscosity. We'll start by looking at a schematic where we show the viscosity as a function of shear rate for a narrow molecular weight distribution. And these types of materials tend to have a relatively sharp transition to the non-Newtonian flow shear thinning behavior. When the distribution changes, it affects the point at which the onset of shear thinning takes place. So if you have a broader molecular weight distribution, there is an earlier onset of shear thinning, but without a dramatic effect on the zero shear viscosity. And we'll see that with an example, same SBR material, but looking at different molecular weight distributions over here. The curves in blue show different molecular weights. They've all been reduced, normalized by the zero shear viscosity for easy comparison. And you can see that anything that has a narrow molecular weight distribution essentially collapses onto the same curve. It's a sharp transition to that onset of shear thinning behavior, whereas the red curves have a broader molecular weight distribution, and you can see it's a more gradual transition. And this is important because if you are working with a material that has a broader molecular weight distribution, as you enter that shear thinning region, it's going to require less amount of energy to pump it through your extruder, and it's important to characterize for those types of reasons. So the previous slides have all talked about viscosity and effect of molecular weight and molecular weight distribution on viscosity measurements. But one of the key advantages of working with a rotational rheometer is that it gives you access to viscoelastic information. And the way we characterize that is through a frequency sweep on a polymer melt. There's an ASTM method for this. It's the ASTM D4440 method. And what that tells us is it quantifies the time-dependent viscoelastic response of a material. So recall that materials that are perfect solids have storage modulus that's dominant. Materials that are liquids tend to have the loss modulus or the viscous component as the dominant component. Here in this example, we'll have 3 different molecular weights or grades of silly putty with dye in them. And silly putty is a classic viscoelastic material. If you roll it up into a ball and bounce it on the table, it's going to bounce back just like a solid. It's got elastic behavior. But if you leave it on the table or inside a container, it is going to eventually flow and assume the shape of that container, which is classic liquid behavior. And the frequency sweep gives us quantitative tools of this type of behavior because it changes the time scale of deformation, going from high frequencies, which is short time scale of deformation, to low frequencies, which is long time scales of deformation. So we'll look at the PDMS example and how that relaxes as a function of across time. And we'll see that the blue sample starts to lose its shape, it holds its shape a lot more better than say the yellow sample, which starts to deform a lot more than the blue sample. And the red sample that's in the middle is somewhat intermediate between these 2 grades. And this type of behavior can be quantified through a frequency sweep because we can look at the point at which the crossover takes place between the storage and loss modulus. Again, I call your attention to the high frequency part of the curve first. This is a point at which all 3 grades of molecular weight the black curves, the storage modulus is dominant. So it has solid-like behavior at very short time scales. And then if we look at the very low frequency all the way towards the left of the curve, in each of these cases, the red curve, the loss modulus is higher than storage modulus, which is liquid-like behavior. What the crossover modulus quantifies is the point at which this transition takes place between solid-like behavior and predominantly solid-like behavior and predominantly liquid-like behavior. And that is a reflective of the time scale of chain relaxation within the polymer melt. So as you start to increase the molecular weight, you're now dealing with longer chain lengths, which means you have greater relaxation times. And longer times means that the crossover frequencies shifts to lower and lower frequencies. And the arrows call out attention to the point of crossover for the lowest and the highest molecular weight studied in this data. And you can see there's almost 2 orders of magnitude difference between those two. The higher molecular weight takes a much longer time to relax than the lower molecular weight. In fact, we did some measurements on the 3 grades of silly putty shown in the schematic here, and sure enough, the yellow had the highest crossover frequency, shortest time scale, compared to the blue, which had the longest time scale. The other feature that I'd like to call attention to is the characteristic scaling in the terminal region for linear polymers. And what I mean by that is, if you look for linear polymers, the storage modulus scales as frequency squared, has a constant slope of 2 at very low frequencies, and the loss modulus scales as according to the frequency or with a slope of 1. And that, once we access that terminal region, we know that we are probing the relaxation of the material, and any changes in that terminal region is very sensitive to picking up differences between molecular weights. It's sensitive to picking up signatures of other things that might be present in your material. For example, if you have blends. And so that's the reason why the frequency sweep is a powerful tool for understanding these types of behaviors in polymer melts. And rheology is very sensitive to high molecular weight contributions. So here we have a set of 3 panels that I'll show that will come up in the following slides that directly compare GPC with rheology data. We'll start with a neat polymer, a low molecular weight polystyrene that has a single peak in the GPC profile. And if you look at the rheology, we have gone down to low frequencies where we are entering that terminal region that was highlighted in the previous slide. If we start to add a little bit, just about 1% of a high molecular weight component, the GPC trace is essentially unchanged, but we start to see some big differences in the rheological profile. We see, especially at that low frequency end, where things are now starting to change, we start to deviate from the terminal region behavior that we saw when we were just having the neat polymer alone. And then if we bump up the concentration to 4%, now GPC starts to show a small bump, not a whole lot, but the rheological profile clearly shows a very different response than the neat polymer alone. We start to see additional crossover points come into play, and the material has deviated from that terminal region that we saw when we just had neat polymer. What this highlights and tells us is that the low frequency behavior is dictated by the highest molecular weight component that is present in the material. And so that starts to have an impact because that now essentially slows down the entire system and types of relaxation that it's going to have. And this has impacts on processing too. So we'll highlight that with an example on how we can understand surface defects during pipe extrusion. So these are 2 different grades of HDPE. One had a smooth surface, the other had a very rough surface. And we start by looking at the complex viscosity data alone. These are shown in the open symbols to the top of the curve. Essentially, the 2 are very similar. There's nothing that sticks out as showing this is the reason why these 2 grades process very differently. But if we look at the storage modulus in the fill symbols, we can now start to see differences between these 2 grades, especially at the lower frequencies. And that tells us that even trace amounts of a high molecular weight component can have an outsized impact. And the reason for that is once you have a high molecular weight component, the entire structure takes a longer time to relax, which means after you finish extruding the product, it's going to take a longer time for any surface defects to relax and get a smooth surface. So one way of handling this, if you have this type of an issue, is to process the entire batch at a higher temperature. But of course, that requires additional energy and, of course, all of the troubleshooting that comes with trying to understand what this problem is. And Rheology can be a valuable tool in those types of studies. Right. So, so before we move on to other topics, I just sort of mention briefly that Rheology can be applied not just to homopolymers, can be applied to blends as well. And we'll have a few, I'll call attention to a few resources that TA Instruments has for that in terms of webinars towards the end of the talk. But again, extrusion is not the only way of processing polymers. Branched materials are often processed in different ways. And extensional flows are critical to understanding this type of behavior, especially if you're dealing with fiber spinning or blow molding. And in these types of applications, a small difference in the long chain branching can make all the difference between a successful or a failed batch because it can have an outsized impact on the processing. So how can we understand this? We can use extensional rheology to identify long chain branching because it is very sensitive to polymer chain entanglement. And on the rotational rheometer, these types of tests can be done using the extensional viscosity accessory or the SCR3 device. And what these devices do is they convert the rotational motion of the rheometer into uniaxial extension, which then allows you to characterize this behavior. It's a very quick test. It takes less than 2 minutes to do. And it's a powerful test, and we'll have examples of that. The comparable approaches that are available would involve some sort of a wind-up device that's sitting at that applies uniaxial deformation at the end of an extruder or maybe a capillary rheometer. And the amount of material that's required to run those devices is relatively high. You need several tens of grams of material. It also takes time to do that, especially doing this through an extruder, then it takes more time. And of course, not the cleaning that's associated with it. With the extensional rheology device, it's a simple device that attaches to your rheometer. It requires samples that are only about 10 by 40 millimeters in size, so very small samples, and the test itself is very quick. So what does it show? This type of test shows a clear difference between linear and branched polymers. And in some cases, it's a lot more sensitive than rotational rheology. So the plot on the left shows a linear polymer, and we can see we're testing this at different extensional rates, and all of these curves collapse right onto one another, indicating that there's no branching in this material. We move over to LDPE, which is a material that has branches in it, and we can see the behavior is completely different. We observe that strain hardening effect, and once we overlay all these curves, as the strain increases and the strain rate increases, at one point the elongation of viscosity is going to shoot up dramatically, and that has clear implications for processing. In some cases, this is a desirable behavior. In other cases, this is not desirable. And extensional viscosity is a powerful tool that helps you understand and characterize incoming batches before you run it through your process. So extensional rheology is a very sensitive measurement, and I'll highlight that with two examples. The first case, we look at 4 different grades of LLDPE. 2 of these have the same melt index. These are samples C and D, shown in green and purple. The melt index is the same. The zero shear viscosity determined through rotational testing is also the same. But if you look at the extensional viscosity profile, that is completely different between these 2 materials. So that tells you there is some subtle difference in the branching between these 2 polymers. The other 2 materials, samples A and B, have very similar zero shear viscosities, but they have very different melt indices. And sure enough, they process very differently when you're subjecting it to elongational deformations. So this is one example that shows the sensitivity of extensional viscosity measurements. The second example shows how sensitive it really is. And here we're looking at 2 different types of HDPEs. that only differ by 2 side chains per 10,000 carbons in the backbone. So very, very small difference. And of these two types, type 1 is the one that has those extra 2 side chains per 10,000 carbon. And immediately through extensional viscosity testing, we can see that it shows strain hardening, a significantly higher strain hardening than the other type. And understanding this information is critical when you're dealing with operations like film blowing or blow molding. And extensional viscosity is a powerful tool to help you get that information. And again, we have some resources on extensional viscosity measurements that I'll call attention towards the end of this talk. We'll switch gears a little bit and move from processing to final product performance through solids. And so this, to understand this, we will use DMA or dynamic mechanical analysis, which quantifies solid mechanical properties as a function of temperature. So in general, DMA is an excellent tool for looking at how the modulus, whether it's storage or loss modulus, changes as a function of temperature when you're dealing with solids. Rheometers are excellent for looking at very soft, flexible solids to melt and liquid-like behavior. And through DMA testing, we get additional insights into the final product of the solid, and we can tie that once again back into the molecular structure. So the most important test, most common test on a DMA type instrument is a temperature ramp, where we look at the storage and loss modulus as a function of temperature and understand the transition point that takes place. So I'll call attention to the right-hand side of this plot at temperatures above 50 degrees. The storage modulus shows a catastrophic drop in its magnitude, almost 2 to 3 orders of magnitude. The loss modulus goes through a peak and then starts to drop off, and the tan delta shown in red has a very distinct peak. These three changes are all signatures of the glass transition of this material. And the glass transition directly correlates with molecular mobility. So what does glass transition tell us? Below the transition temperature, all of the chains are essentially locked in place with very little thermal energy to have movement. And in this state, the material has a very high modulus on the order of 10 to the 9 pascals. It's a brittle, glassy state. And then above the TG, the material becomes soft and flexible, and the modulus decreases significantly. So if we take a piece of elastomer at room temperature, it is very soft and flexible because we are in the rubbery plateau region. It's a rubber after all. But if we were to place that same piece of rubber in the freezer, it becomes a rigid solid because it is now in a state that is below its glass transition. The molecular mobility is essentially arrested. For polymeric materials, at room temperature, they are rigid solids. And then as we heat them, they start to enter that rubbery plateau region. And if we continue heating past that temperature, we eventually enter the melt region, which is where all of the processing happens. So glass transition is essentially the cooperative motion among a large number of chain segments in your material. But in addition to the glass transition, which is that primary peak that we see in the profile in tan delta, there are other transitions that can take place at lower temperatures. And each of these transitions are identified as secondary transitions, and that comes about due to local or side group motion, or it could be due to the presence of small molecules like plasticizers that you have added into your material. And as a technique, DMA, this type of a DMA scan, is about 100 to 1,000 times more sensitive than DSC for identifying weak amorphous transitions, because amorphous materials have a very small impact on heat flow, which is what the DSC measures, but can have an outsized impact on the mechanical measurements, which is where DMA is measuring. And we can monitor the glass transition using DMA to help us understand blend miscibility, cross-linking, crystallinity, and so on. I won't talk in detail about blends, but I'll just call attention to the one plot that we already have on the screen. This is a plot of ABS, which is a blend of butadiene and styrene. It's an immiscible blend, and when you're working with immiscible blends, each component retains its own transition through a peak. If it's a miscible blend, all you would see is a single peak that is somewhere between these two materials, depending on the mixing ratio and the chemical affinity of those two components. So we'll look at just one example on how the glass transition can be affected by the structure, and we'll focus on crystallinity alone. So for polymer materials, they could either be a completely amorphous material, or maybe they could have a crystalline structure. And the way crystallinity affects the TG is crystallites act as a cross-link within the polymer matrix. And so this makes it behave like a cross-link network, but because the cross-links are not permanent, they can change as a function of temperature. As you heat and increase the temperature, these crystallites melt, and the material undergoes now a progressive change in the structure until the melting point. And glass transition is measuring the mobility. So as you start to have greater amounts of crystalline structure, the mobility is restrained. So one way to visualize crystalline polymers is its mobility is restrained. So one way to visualize crystalline polymers is it's as a multi-phase system that has an amorphous phase with some dispersed crystalline units. And the crystalline units are now restraining the mobility of the nearby amorphous regions. And as you increase the crystallinity, it increases the glass transition. It decreases the peak of that glass transition peak because different crystalline domains have to melt at different points. And it has an effect of broadening the overall transition temperature range itself. So we look at an example using PET. So we've looked at 3 different grades of PET with differing levels of crystallinity. Visually, these samples A is completely amorphous, that is shown in the lower right, and C is crystalline, which is completely opaque. And we can pick up signatures of the level of crystallinity through the DMA test, both in the storage and loss modulus. We see a
Thank you,
systematic
Bharat,
shift
for that
in the
great
onset
presentation.
measured through storage modulus.
We do have a little bit of time now to answer some questions that were submitted. And before we do, I'd just like to let everybody know that this particular webinar and all the webinars that we have in our various series, notes, and other resources that are available on our website. So we have a number of questions here. I'll say that some of the questions will probably just simply relate to you or respond to you via email. They definitely are a little bit more detailed than what we're going to cover here. But there are some good questions here that I think that we can answer. So the first peak height of the tan delta peak.
And at TA, we've recently introduced the new Discovery Hybrid Rheometer that is powerful and versatile and delivers very sensitive measurements with simplified user interactions. So we'll just spend a couple of minutes looking at how this can benefit your lab. At the heart of the rheometer is technology that is very unique to TA. We use a patented magnetic thrust bearing that gives us exceptional low torque sensitivity. Traditional rheometers tend to use air bearings, which is low friction, but the magnetic bearing takes it one step further, where the system friction is now reduced by over 70% compared to traditional designs. We combine that with an advanced drag cup motor patented by TA that delivers excellent torque accuracy with enhanced low torque.
So the next question that we have here is,
and for polymer testing,
does
this matters
TPS really simulate real life?
Viscosities, lower molecular weight materials, or operate at higher temperatures in cases where the viscosity is very low, and get more accurate data across all of these conditions. And this is then paired with an exclusive optical encoder dual reader that measures displacement. Displacement, having access to excellent displacement is critical to getting G prime and G double prime values with confidence. And improved phase angle precision is on the order of about 70% compared to single reader designs based on the technology that we have in the Discovery Hybrid Rheometers. This directly translates to more accurate G prime, G double prime measurements or tan delta at very low stresses or with challenging samples, whether they're extremely stiff or very, very soft. And we also get more accurate displacements at lower strains. And we look at one example of the direct benefit that this brings into the lab. So we're looking at the curing of a thermoset resin, and these types of materials can be somewhat challenging to study on the rheometer. They start off as viscous liquids that cure to very rigid solids. And we're showing a direct comparison between the dual reader technology in the fill symbols and a traditional single reader, and we can see across the entire spectrum, we get cleaner quality of data, especially on the phase angle. The dual reader technology helps you to accurately measure the weakest elastic structure before cure, the G prime, where the material is primarily viscous liquid, and accurately pick up the smallest traces of the loss modulus when the material is rigid solid. So the dominant component is easy to measure on most rheometers, but when we have this type of advanced technology, it allows us to pick up the weakest traces of viscoelastic behavior, and that can be critical when you want to get to that low frequency terminal region and accurately get the storage of the loss modulus under those conditions. And here is a quick comparison of the waveforms that one encounters at low frequencies, even though, or in the early stages of the test, even though there's not a big difference in the waveforms, the dual reader delivers better quality data. And then at at times after the material has cured, you can see that the dual reader delivers much better quality of the waveforms, which gives a visual representation of the stress and strain that's being applied compared to traditional single reader approaches.
So the next question is peak in
and
the
one
tan
of the biggest
delta,
advantages
peak
of
in the
the
G
Discovery
prime.
Hybrid Rheometer is it allows you to go
The
beyond
second part of that
traditional
is,
shear rheology, because
it
it also
we see
offers
some differences
integrated
between the
DMA
TG determined by DMA versus DSC.
enabled by
Is one
pattern magnetic
more right
technology that
than
we
the
spoke
other?
about earlier, and FRT, or
Discuss that a
force
little bit
rebalance
further.
technology that delivers the most accurate normal force measurements on rotational rheometers. And because this is integrated into the rheometer, it does not require the installation of external components. You can switch between shear measurements and DMA measurements in the order of minutes, rather than several minutes where you have to take, disassemble and reinstall components on other instruments. And this capability allows you to measure the storage and loss modulus, E prime and E double prime, and tan delta. And we've seen some of these advantages of measuring those. The reason we call them E prime and E double prime is because we are now making measurements under tensile deformation, compressive deformation, or bending deformation with 3-point bending or single or dual cantilever geometries. So it can be, it's compatible with a full range of DMA geometries. Temperature control is provided by the oven that can get down to temperatures as low as -160 to as high as 600, and can be paired with liquid nitrogen-free mechanical cooling down to temperatures as low as -85. And this feature is included on every HR30, and it's an optional add-on for the HR20 model. And all of this advanced technology is paired with ease of use. The Discovery Hybrid Rheometers can be used with Trios software, and Trios Autopilot is a premium package for Trios that delivers complete workflow automation. It allows you to centralize, streamline, and standardize operations from the R&D lab to the QC lab, so that everyone is running the same procedures, ensuring SOP compliance across different sites, reduce the need for operator training, and automate advanced calculations within the procedure. And it does this through a combination of a simplified interface and guided instrument operation. So a view of the interface, simple interface is shown in the lower right. All the operator does is to select the test that they would like to run by clicking on one of these icons from a pre-selected list of options.
Our lab sends out samples for DMA testing to an external lab for occasional analysis. With this new rheometer, can we do both types of testing on the same analyzer?
Text boxes, and then at the end, when they're finished, it does an automatic analysis, generates a report, and brings them right back to this. So it's guided operation from start to finish, and it's excellent for rolling out test methods that are developed in R&D sites out into QC production sites across the world. And there is a separate webinar on Trios Autopilot, and I encourage you to check that out. It can be accessed through the virtual trade show page. With that, we sort of highlight the advantages of the Discovery Hybrid Rheometer. It delivers excellent sensitivity for the greatest measurement accuracy. It's easy to use,
one final
right
question
experience
here.
for every user, whether they're an advanced rheometer user,
if we look
scientist,
at extensional
or
rheology,
an operator that is using a rheometer as part of many instruments in a QC type setting, and has unrivaled versatility because it gives you 2-in-1 instrument capabilities within the same instrument. I'll close out by calling attention to additional resources that are available from TA Instruments. So we have guest webinars on a wide range of topics. 3 topics that are relevant to polymer processing are ones by Professor Chris McCosco, Professor Joao Maia, and Martin Sentmanat on the topics of molecular weight distribution, polymer blends, and extensional rheology, respectively. And we also have a series of over 50 videos that are tech tips, not just rheology, thermal analysis, every technique that TA offers, and this can be quick and easy way of training people in the lab. And we also have seminar series, the Incident Insight seminar series that are topical, focused on.
Like I said, there's a number of questions.
There's one on thermoset
Thank everybody
that
for their attendance today. And
as Rob
already mentioned, stay tuned for more webinars from TA Instruments, including tomorrow's webinar, Grace Lau on the column analysis using new multi-sample DSC. It's 11 o'clock Eastern US time. And then also just make sure, as Bharat mentioned already, make sure to check out some of our other virtual events at tainstruments.com, including some opportunities. And we look forward to you joining us for any other future events. Thank you.
And then in 2 weeks from now, we will have a live demonstration, a virtual demonstration of the new Discovery Hybrid Rheometer. I encourage you to sign up for that. We will be taking questions live, and you can see the rheometer up close in action. And with that, I thank you for your attention, and I'm happy to answer any questions. Sure. The tan delta is a measure of damping of the amount of energy that is dissipated through as the material goes through the transition. So materials that have a greater peak height, tan delta peak height, are now dissipating more energy as they go through that transition compared to other materials. So if we go back to our example, I'll go back to a few slides. The amorphous material has a much higher tan delta peak compared to the crystalline semi-crystalline materials. And that tells us that the amorphous material is now going to be a lot more flexible as it goes through the transition and after that transition compared to any material that has elements of crystallinity to it. Sure. So TTS is a technique that is very well established in rheological literature. There are several publications that have gone in depth into detail on this topic. And TA has apps notes on this as well, but there are also many peer-reviewed publications that are available. As a technique, it works, but we have to be careful when applying TTS. So it works under some simple conditions, but there are a few cases where it should not be used. Specifically, it should not be used if any crystallinity is present, if the actual structure is changing with temperature. For example, let's say you're going through a temperature range and you start to have a cross-link reaction. TTS would not be advisable in those conditions. TTS does not work if you're working with block copolymers. It can work maybe within a limited temperature range, but more often than not, you need more complicated types of analysis. And then it works on simple materials. If you start to have a composite of different materials, there are some cases where TTS holds. Usually it works when you have the temperature sensitivities of both materials are very similar, or they have very close activation energies. So examples of miscible blends where TTS can be applied would be PPO and polystyrene, PMMA and PVDF. Immiscible blends where TTS works, ABS, polycarbonate and polystyrene polycarbonate mixtures, polyethylene and polypropylene. So those types of materials, it tends to work. It fails in a lot of other cases too. So it fails when you have a big difference in glass transition of these individual components of, if it's the larger that difference, the greater that difference, the greater the likelihood that it will fail. It has been seen to work in some cases where the delta between these two is as high as about 50 degrees, but one must exercise caution in using TTS. So examples of places where it would fail would be miscible blends, PEO and PMMA. TTS does not work. Immiscible blends, polystyrene and PMMA, or polystyrene and LDPE, it does not work in those cases. So I'd exercise caution in first checking out if there's literature to see if TTS is suitable for this material, if there's any published literature. See if the curves shift easily, or if there's additional or more advanced analysis that are required. And again, refer to the body of work that's already published or and TA's apps notes on this topic. Sure, that's a very good question. It's one that comes up commonly. So there are three signatures that are associated with the glass transition. So on this plot, if you focus on the right-hand side, that's where the glass transition is taking place. And that shows up as a significant drop in the storage modulus, a peak in the loss modulus, and then a peak in the tan delta. Our guidance is, at TA, we tend to report glass transition through the tan delta peak, but by no means is that the right or the only way in which this has to be reported. What is important is for consistency in making sure when you compare values, glass transition values from across different either published literature reports or maybe across different sites, is to make sure the conditions are specified. How is this glass transition being measured? Is it being reported based on a tan delta peak, or the storage modulus onset point? What is the temperature ramp rate, and what is the frequency at which this is being tested? So all these three things have to be reported to allow some sort of comparison across one site and the next. And again, there is no correct answer. Again, we tend to report it in terms of tan delta. From an engineering perspective, the onset point might be preferable because that is a point at which the modulus starts to drop off, temperature at which starts to drop off significantly, and you want to stay, several degrees below that to make sure the sample does not lose its structural rigidity. The onset point calculation can be subjective. It depends on the limits that you have, and that's why we recommend using the tan delta because the peak is more or less unambiguous. I think the second part was about relating DSC and TGA, or TG between DSC and DMA, sorry. The two techniques are a little bit different. A DSC measures glass transitions as a heat flow event. The DMA measures glass transition as a mechanical change. And the two may not coincide with one another. In fact, in most cases, what we observe is that the TG from DMA tends to be higher than the one measured from DSC. So that is expected, and that is not surprising at all. Yes, absolutely. So that is one of the biggest advantages of the new Discovery Hybrid Rheometers, is that it gives you two-in-one instrument capabilities where you can seamlessly move from shear testing of your polymer melts, getting your frequency sweeps to look at the rheology and the melt viscosity, into looking at glass transition of solids by simply just changing out the fixtures. And it's great for anyone who has occasional testing. You can now bring in this test capability into your own lab. And it does not require a standalone separate instrument. It's only a marginal investment in the tools and geometries to get that capability. Sure. Extensional viscosity measurements, the drums that are used in, and I will go to the specific slide so we can visualize this. The polymer is attached onto those two drums, and the standard accessory is supplied with smooth face drums. And if you have issues with slip, one thing, of course, you could try to change the temperature, but you could also opt to buy roughened or knurled drums. They just drop right into the device. It's easy to swap them out, and adding that little bit of texture or surface roughness might help with your material to adhere to that surface and stick as you go through and make these measurements. So that might be something to consider.